Okay, so now in this video, we're going to discuss more about plate height and column efficiency during analytical separations by now focusing on the Van Deemter equation. And Van Deemter is going to be sort of a conceptual equation that we use. It could be a calculation-based problem, but primarily the concepts that it describes are contributions to band broadening. And I'll define band broadening here for you. So by a band, we're referring to essentially a range of retention times for a given compound. So band broadening would be, for example, if you were to see a peak on a chromatogram where you have time on the independent axis, and this peak has some width at the baseline, W sub B, this difference here. And if you were to have a different separation where now that peak is altered and the compounds of this type come out over a wider range of retention times, it would look like this, right? Where now the width at the base, of course, is much larger. So this is what's meant by band broadening. This process of the peak undergoing some widening event or a compound eluting over a broader range of retention times. So the three different terms that can lead to this band broadening are the A term, which is known as multiple paths. And there's also a B term that is inverse with the flow rate. So recall that the linear flow rate U sub x is how fast the mobile phase proceeds through the column. And that usually has units of some length, like centimeters per time. So the B term, or formerly known as, B over flow rate, this is longitudinal diffusion. And finally, the third term that contributes to band broadening or peak widening is the C term, which is referring to a linear dependence on flow rate. And this is known as resistance to mass transfer. So all of these terms are going to cause band broadening. And what that means is it will increase the plate height, right? They all are factoring into the total plate height of the separation. Remember that plate height, if it increases, the number of plates will decrease, and the resolution will decrease since it's proportional to the square root of n. So we always want to minimize each of these terms, and sometimes we can eliminate one entirely. And so we're going to talk about, exactly what each of these terms means, in what situations they apply, and when they are not present. But you can never eliminate all of them. There's always a Van Deemter equation for any associated separation technique. You should know just a couple synonyms. Multiple paths is also known as eddy diffusion. And the C term, the resistance to mass transfer, is also known as finite equilibration term. So let's now go through each of these types of band broadening and discuss how we minimize it, and first how it's broadly defined. So the A term, or also known as the multiple paths term, this only applies to packed columns. So I'll show you two different setups here. For an open tubular column, remember that you have some film of sort of a gel-like but liquid stationary phase along the inner wall of the column. And the mobile phase, which I'll indicate here in blue, is simply going to flow straight through the column and take the solutes with it. And the solutes will go back and forth and stick to the film, depending on their relative affinities for the stationary phase. So when a solute is moving through the column, let's say we have two molecules of X, okay, when they're moving through the column, there is simply one path. And that one path is straight through the mobile phase, right? This column is basically hollow, or the stationary phase is not packing it and not providing any irregularity of route. So multiple paths means that in a packed column, or the A term is 0, there are multiple paths that a single solute, like type X below, can take. From the entrance to the exit. So what this means is it's going to lead to multiple or possible flow velocities that range, right? Or the retention times of compounds will be arranged because they are going through the column at different speeds. So, of course, we want to separate compound X from other compounds in the mixture like Y, and we want those to come out at a range of retention times, but you do not want multiple flow velocities for a single compound. Because then, if some X molecules are coming out early and others are coming out late, simply because they can take multiple paths around the packed stationary phase, then that's going to decrease the resolution or widen the peaks. So let's consider now that packed picture where we have stationary phase bead particles of a variety of sizes, packed maybe uniformly or not. And as the mobile phase enters this packed column, now it's going to once again carry the solute with it, and the solute will stick to these individual beads for varying amounts of time, depending on the polarity, sometimes other characteristics like charge. We'll discuss those later, but just know that maybe molecule X here will take this path through the column, and perhaps molecule Y, or let me use another X since we're talking about a single solute separated from itself, but I'll use a different color. Maybe this X molecule spends less time in the stationary phase or takes a very direct route through. Okay, so those are going to have different TRs or retention times just for molecule X alone. And molecule X should really come out all around the same point in the separation, because molecule X, it's identical to any one of its counterparts, or it should have the same characteristics and should stick to the stationary phase with the same affinity. So we do not want this optional case of having multiple flow paths. It's bad for resolution, okay? It gives different flow velocities for a single compound, right? Or leads to what's called eddy diffusion. In open tubular chromatography, when the solute is moving, when it's not stuck to the film of stationary phase, but when it's moving through the column in this direction, it just goes straight through, right? There are no beads to encounter like there are in a packed column. So here, now the X molecules have the same retention time, assuming that they stick to the stationary phase for the same average amount of time because they are the same molecule X. So once again, when you're separating compounds, you want different molecules, X and Y, to come out at different times, but you want the X group, or the collection of molecules that are all the same, to come out at a very narrow range. So here we'll have a narrow peak if we have a small range, or basically the same retention times. And you'd have a much wider peak, or a low resolution experiment would take place if you have the packed column. Now, as we've discussed before, that although the open tubular are more efficient because they minimize this multiple paths term, or the multiple paths term is 0, which means the Van Deemter equation just becomes B over flow rate plus C times flow rate. It's only 2 terms, which we will move on to next. Open tubular are more efficient, or you generally get better resolution, okay? Higher plate number and lower plate height. But the packed columns, we saw that these had more available stationary phase, and a greater surface area of stationary phase means you can add more solute to the column, or they have a greater column capacity. And that's often useful when you're trying to separate compounds after a reaction or something. Okay, so for a packed column, you can optimize the A term, but we can never make the A term 0. A is always positive. There's always more than one route through this irregularly packed stationary phase. If we can make it more regular, then there will be fewer places where a solute might spend a much shorter or longer time than another solute of its same type. So we want to make the stationary phase uniformly packed. The solution to doing that is to decrease or minimize the bead diameter. The smaller the beads of stationary phase, whether they're silica or alumina, the more uniformly packed they will be. And now you'll have fewer irregularities causing changes in flow velocity. And therefore we get a lower number of plates and minimize A. So decreasing bead diameter will decrease the number of possible paths through the column. Additionally, for a packed column, the flow rate is not going to affect the A term. Okay, so A is not even present in open tubular, and in packed, it's simply a constant. So once the stationary phase and the mobile phase are selected, then A is a fixed constant. In other words, once that stationary phase bead diameter is chosen, there's no way of getting around the uniformity of that specific bead diameter. If you were trying to make a more uniform packed column, you would have to purchase a bead of a smaller size and pack it very carefully. So what that means is this is the A term, or the only term in the Van Deemter equation, which is mobile phase flow rate independent. So the B term does depend on the flow rate. And we discussed earlier that the name of this term is longitudinal diffusion. So let's talk about what that means now. So longitudinal diffusion just says that compounds are going to randomly diffuse along the length of the column. And they do so with no rhyme or reason, right? But simply the second law of thermodynamics says that the entropy of the universe must increase, or disorder must increase for any reaction or process to be spontaneous. So compounds diffuse away from one another and disorganize one another in a spontaneous manner. And they do that in all directions. We're primarily going to focus along the longitudinal axis, or the axis that is parallel with the direction of the mobile phase flow rate. So if the mobile phase is flowing here from left to right, and if you have two compounds, let's say we have this compound X and compound Y. Early on in the separation, let's say 1 minute in, you'll find that compound X and Y are separated by how fast they are flowing through the column, one faster than the other. Here I'm showing X moving faster than Y, so Y must have a greater affinity for stationary phase. So if they're flowing in this direction from injector to detector, molecule X is not just going to flow that way. Some molecule X are going to come backwards and diffuse in all directions. Okay, so that's going forwards towards the detector and backwards, which causes over time the band to broaden. Or some X molecules will be further ahead, others further behind. If you were to take a snapshot maybe at 10 minutes in the separation as opposed to 1 minute. Okay, and then molecule Y would be also more dispersed, lower density here, and those bands would start to overlap. So molecule Y is experiencing the same random diffusional processes below. So here we would have good separation, okay, or high resolution. But now, because of this overlapping, we have low resolution, or the peaks widen. So the B term, or the more these compounds diffuse along the column, and the longer they have as time available to sit there and diffuse, they are going to spread out. And that spreading out process increases the plate height, decreases the number of plates, and decreases the resolution. So it's always impossible to eliminate diffusion, right? Diffusion happens, and there's a diffusion constant or coefficient that helps to describe this for each compound. So we can never eliminate the B term. This would violate thermodynamic principles. So in every separation, even in really, really high efficiency techniques like capillary electrophoresis, the B's term still survives and is a contribution to band broadening. Okay, sometimes we can alter the stationary phase, and that will help to eliminate a term, or we can even get rid of the entire stationary phase. But this term here is due to the solutes themselves. And you cannot tell those molecules not to diffuse randomly. That would violate thermodynamics. So there are some different ways that we can try to minimize B. And one of those is by minimizing its time spent on the column, right? So if you decrease time on the column, or the time that the molecules are in the mobile phase for, also known as the resonance time, then that means we're going to have less diffusion, because diffusion is simply, right, an entropy increasing process where it extends and increases infinitely with more time, okay? Molecules spread out from one another randomly. So the less time in the column, the less these two peaks will widen and look like this XY picture here. Right, remember at our earlier snapshot, 1 minute, those compounds were pretty separate from one another and not overlapping. So to affect the time spent in the column, that means that we should increase the flow rate. If you increase the flow rate, then you will decrease the resonance time. And that will cause lower diffusion. So notice that in the Van Deemter equation, the B term is B over flow rate. Okay, or it's inversely proportional to flow rate. Okay, or higher flow rates means less diffusion, means lower number of plates, or sorry, lower plate height, higher number of plates results from that. Lower H and higher N. So now you can also think about the temperature at which the column is run. Okay, so sometimes it's optimal to do these experiments in a cold room at 4 degrees Celsius to minimize diffusion. So increasing temperature leads to an increase in the average kinetic energy, right? Kinetic energy of a compound or a gas primarily, but you can also think about things in the liquid phase, is related to the velocity here. So at higher kinetic energy, we have higher velocity, and therefore compounds are moving around at higher diffusional rates. So we always want to minimize diffusion or minimize the B term and operate that experiment at a lower temperature. Because of this, the B term is most problematic in gas chromatography. Because GC, of course, is an elution method where we have a gas mobile phase, and we oftentimes have to crank up the temperature, right, to several hundred degrees Celsius to vaporize and elute all of the volatile compounds. So GC is operated at high temp, and therefore usually has a very large contribution to band broadening from the diffusion, or the B term, which increases at higher temperature. So finally, heavier compounds, which of course you can't choose the molecular weight of the compound you're working on if you're trying to study something specifically, but the molar mass of the compound you're stuck with and trying to separate, if that increases, right, or we have a larger size of the molecule, then the diffusion coefficient, D, is going to go down. So heavier compounds, these just diffuse slower. Now do not mistake this capital D with the distribution coefficient that we talked about for organic acids and bases later or earlier on. This is a same variable used for different meaning and you should be able to recognize it, but primarily you'll just be using it for conceptual means, and rarely will you do a calculation with the diffusion coefficient. So lower diffusion coefficients, those compounds are going to have lower B terms and therefore lower plate height and a higher number of plates. So now, perhaps the most conceptually difficult question or question to be asked about the Van Deemter equation is interpreting the C term. So we said C was the resistance to mass transfer. And that resistance to mass transfer is going to be a bad thing, right? Now, mass transfer, this is partitioning. And we'll recall what a partitioning event is below. So if you have compound X and it's in the mobile phase, if it equilibrates with X that is bound to the stationary phase, right, then at some constant ratio of concentrations of X in stationary relative to mobile, you reach this equilibrium constant or K part. And partitioning allows solutes to separate out, such as solute X and solute Y to separate. And we said that we always want, for the optimal and efficient separation, we want the maximum number of these partitioning events so that the column can do its job. And because compounds X and Y stick so many times, they can tell a very small difference between the structure of X and Y, and they will come out at different times. It will separate well if there are lots of sticking events. Okay. So we do not want resistance to this. The resistance part is what's bad. We do want mass transfer to occur. And the higher the resistance to mass transfer, the higher the C term will be, and that will affect the plate height. So if we think about this column, right, we have our stationary phase. Let's just say that the stationary phase is for an open tubular column. It's along the inside wall, simply a liquid gel-like film. And we want X to be able to go back and forth with that stationary phase as many times as needed until the column is able to efficiently distinguish X from Y and separate them or elute them at various retention times. Okay, so this is the idea of mass transfer or equilibration. So equilibration, or reaching an equilibrium of X and Y in stationary relative to mobile phase, that's going to require time, or it's finite. And we want to minimize the time it takes so that it's very fast and efficient to partition, so we can get as many partitioning events as possible. So if you have a higher amount of time, a longer amount of time, I should say, spent on the column, then there will be a larger number of partitioning events. And therefore, there will be less resistance to mass transfer, or you'll have more X and Y partitioning events to separate the two compounds from one another. So you decrease the C term, which will decrease the plate height and increase the number of plates. Less resistance to mass transfer, if given more time to do so. So the mobile phase flow rate was going to directly affect this time spent on the column, right? If you have a lower flow rate, then there will be more time spent on the column. And as I outline above, the C term will go down. There will be less resistance to partition, and the number of plates will go up. So imagine if you were on the sidewalk trying to jump into a moving car safely, right? Is it going to be easier to jump into that car if it's moving 5 miles an hour or 60 miles an hour? And the answer, of course, is 5. So it's easier to go from the stationary phase, the sidewalk, to the mobile phase, the moving car, more times and more effectively if it's moving slower. So slower flow rates allow for more of this diffusion between the stationary and mobile phases, which is a good diffusion that we like. Okay, the diffusion we were trying to minimize was longitudinal diffusion, okay, along the length of the column. And that was the B term here. So the B term was the opposite, essentially. Higher flow rates made the B term better. But now, lower flow rates are going to help minimize the C term. So that's why you see this direct relationship or a linear dependence on flow rate. Okay. So increasing temperature will increase the rate of partitioning, or compounds move faster and they go between the stationary and mobile phases at a higher rate. And that will increase the number of partitioning events, which will in turn decrease the resistance to partitioning, decrease the plate height, and increase the plate number. So the temperature, we wanted it to be low for the B term, but now we want it to be high. So it's often true that the B term and the C term often sort of counterbalance one another. One is really important at low flow rates, and the other is really important at high flow rates. And it's about finding a happy medium between them with the correct flow rate that optimizes the efficiency. We'll see that in a minute. Furthermore, we can talk about the diffusion coefficient of the solutes. And that diffusion coefficient, of course, for heavier compounds of higher molecular weight, you will have a lower diffusion coefficient. And that means you're going to decrease the rate of partitioning. It's harder for the compound to go between the mobile and stationary phases. So that will decrease the number of partitioning events, or there's more resistance to partitioning here. C goes up, which increases the plate height and decreases the number of plates. Okay, so there's two ways we can think about the stationary phase in the context of that C term, resistance to mass transfer. And whether the stationary phase is open tubular versus packed, right? Whether it has a film of stationary phase, some sort of gel-like liquid film on a solid support, or whether it's packed with stationary phase beads, such as silica. You always want to have a thinner film or decrease the film thickness. Now, that's going to limit how much solute can be loaded onto your column, and you have a lower capacity. Or if you have less stationary phase, you have a lower capacity for solute. but it doesn't take as much time for a compound to go to the film, diffuse into it, and then diffuse out. It's easier to go in and out of the film if you have a thinner film. So equilibration or partitioning between mobile and stationary phases becomes easier and therefore faster. That increases the number of partitioning events. So decreasing film thickness is going to cause a decrease in the C term or a decrease in the plate height, and therefore an increase in the number of plates. So finally, if you're using a packed column instead, once again, you want to decrease that bead diameter of the silica or alumina particles that are packing your column, right? If the bead diameter goes down, then we have increased uniformity, or all of the stationary phase particles pack more regularly together. And that's going to decrease the ability of solute to get stuck in the irregular parts of the stationary phase, where maybe it's sort of secluded from abundant mobile phase. There will be easier adsorption processes, or we increase the rate of absorption and partitioning back out. So I should say adsorption chromatography here, because we're using a solid support or a solidly packed stationary phase with no film. And we increase that rate of adsorption and its reverse, or leaving the stationary phase, going back to the mobile phase, if we have lower bead diameters, fewer irregularities in the stationary phase, and greater uniformity. So let me just show you a couple ways to visualize all three terms at once. The Van Deemter plot is the plate height in microns generally, or micrometers. It could be another unit of length, as a function of flow rates, which is generally centimeters per second. Any length per time works. This is linear flow rate. And if you first plot those terms individually, right, the A term did not depend on the flow rate. So once the mobile phase and stationary phase are fixed, okay, A is constant or has a slope of 0. Now, that's for a packed column where it's non-zero. If you had an open tubular column, the A term would be along the baseline. That would be 0. And then the B term was inversely related, right? Or as we go towards high flow rates, that longitudinal B over flow rate goes down, because higher flow rates, the compound spends less time in the column and diffuses or spreads out less. So this is going to be mostly important at slow flow rates. And it's going to be a primary contribution to band broadening, or will make H very large at slow flow rates. So that's why we need to avoid flow rates that are too slow. And the third term is the C term, which is linear with flow rate, C multiplied by flow rate. And this is large or important at high flow rates. And that's when it's going to cause band broadening. So we need to meet somewhere in the middle. And after that stationary mobile phase are selected and the mobile phase flow rate is optimized, then you will have the most efficient separation given the conditions. So if you add these together, you're going to get this skewed light parabola, okay? And you just want to roughly find the minimum here, okay? Multiple flow rates would maybe be okay. So let me make it a little more defined. The Van Deemter plot generally takes on this shape here. How about we say this is the lowest point on the page or on the plot, and therefore our minimum plate height is found on the y-axis, and our optimal flow rate is found on the x-axis. So in problem solving, we will do some. When you're asked to calculate different values for a chromatography experiment and you're told it's operated at optimal flow rate, you find that minimum on the plate height, use it in the relevant equations to maybe solve for other things like number of plates, and then use the flow rate as well to solve for TM, etc. Okay, so we always optimize the flow rate by selecting that at which we have the minimum plate height. So a couple more questions that you could be asked related to the Van Deemter equation include just simply writing the equation and explaining the terms for specific types of separations. So for GC, where you have an open tubular column, recall that there is only one path through the column, and the multiple paths term is 0. Then the Van Deemter equation becomes simply the B term and the C term. If you have LSC, which is a packed column where there's a liquid mobile phase, solid beads as your stationary phase, and you're separating out based on polarity, then all three terms are there. There's no way with a packed column to eliminate any of these. You have three contributions to Van broadening there. Later on, we'll talk about a method which has a mobile phase only, or a buffer. There's no stationary phase in capillary electrophoresis. And there, when there's no stationary phase, now the plate height is just due to the longitudinal diffusion. We can never get rid of that B term because the solutes are predicting that diffusion coefficient, and they always are non-zero, or solutes always diffuse at some constant value at a given temperature. So you can't avoid the B term, even if you get rid of the stationary phase. But capillary electrophoresis, because of this one term in the Van Deemter equation, has very efficient separation ability. Where we can get the highest number of plates and the maximal resolution. Okay, so this was a lot of concepts with the Van Deemter equation, and you could be asked to solve for the plate height mathematically, be given the coefficients necessary. But what's more important is for you to understand each of these concepts for how we describe the three terms that contribute to band broadening, and then how we optimize or minimize each of those, if not eliminate them fully. It's all aimed at minimizing the plate height and increasing the number of plates. So for more practice with efficiency of separation in the Van Deemter equation, you can visit Unit 2 of my analytical course guide at chemguides.com.